Hi, I'm Max, and welcome to this quick video about von Neumann stability analysis with an example using the Lax-Friedrichs method for a simple linear partial differential equation. Okay, so the idea of von Neumann stability analysis is to represent this function u as one Fourier mode. So let's write u of j at time step n. Here is my spatial index, and here is my temporal index, just to make sure it's clear, is e to the I k x and let's see xj, because that's our spatial index. So this is one Fourier mode, and we would like to show that at the next time step, ujn plus 1, our growth factor, it will look something like this. We multiply our same Fourier mode by some growth factor, and we want this to be less than or equal to 1. Because if it's greater than 1, that means that our solution is going to blow up in time. You know, if you multiply by a number larger than 1 a bunch of times, it's going to be huge and probably produce inaccurate results. So the ideal is closer to 1, but less than 1. Okay, so let's try this. So I will put in here, let's plug in our values right here and here. And then we're going to use a little bit of like a little bit of algebra. That will be kind of quick, but then we'll get a nice result to show that the Courant number, which is right here, I'm going to represent this as R equals C delta T over delta X, has to be less than 1 or less than or equal to 1 for this Lax-Friedrichs method to be stable. So that means because there's a condition for its stability, it is conditionally stable. Okay, so let's get started. U of j at time step n plus 1 is written here, g of k at e to the I k x j. I need to finish this j right there, is equal to 1/2. This comes from the finite difference method right here. This u of x, it's kind of like averaging this point here and then taking the difference. So here, let's try e to the I k xj, that will be multiplied by e to the I k h, because this is h more than our point that is our base. So here's the stencil for the Lax-Friedrichs method at time steps j minus, or sorry, spatial steps j minus 1 and j plus 1. We have time steps n and n plus 1 here. We omit the central point, and that lets us have this lovely condition of stability, even though it is a central method. So this difference here is delta x, which I will call h. So delta x equals h. And that means r could be c delta t over h. They're all the same. So then let's do u of j minus 1 at time step n. That will be plus e to the I k x j times e to the I k negative h, because we are now h less than our central point, that is a u, j, and n. So I'm going to put an h but have a negative in front here. Then we have to do this next part together. Let's actually change this to r just because it's a little quicker for us, and that's lovely. Minus r over 2 times e to the I k x j times e to the I k h, just because it is h more than our point, minus e to the I k x j, e to the negative I k h. And then we're pretty much done with this first part, but there's a lovely quick simplification we can do. You'll notice that every single term in this equation has an e to the I k x j in it. That's here, right here, right here, right here, and right here. So we could cancel it. Let's cancel the complex exponential. We can divide on both sides because it's never going to be 0. So that's fine for us to cancel all of these terms. And that makes our equation quite a bit nicer to work with. That leaves us with g of k, our growth factor term, is equal to this all, and it will be pretty cute together. Next, I'd like to bring up a quick equation that will be useful. I'm going to write this one in blue. It is e to the ix equals cosine of x plus I sine of x. If you have a negative in front, you just replace this plus for a minus, and that is because of the symmetry of cosine, but not, sine around 0. Then what we'd like to do is use this idea where x is going to be kh. Right here, you'll notice that this is actually something nice, and we'll kind of derive it together using this formula, but you could skip ahead if you already know where this is going. This right here is going to be 1/2 of e to the ikh will be cosine of kh plus I sine of kh. E to the minus ikh will be plus cosine kh plus I sine, or sorry, minus I sine kh. And what's really neat about this is that the I sine kh is going to cancel because there's one and another, but one is negative. And so we're just left with 2 cosine kh over 2, which is cosine kh. You may know that this is hyperbolic cosine. Okay, and same thing here. Right here, we're going to have hyperbolic sine. You could work through this if you'd like, but just to save some time, sine kh. I'll just write that quick. Okay, so I'm going to erase this just because we don't need that anymore. Now we know that g of k is equal to, right here, I'm going to rewrite the equation real quick so it looks nice, is equal to cosine of kh minus r sine of kh. Hyperbolic sine and hyperbolic cosine inherit this 1/2 term, so that's why we're just left with this 1r. Now we really want to show that g of k is less than or equal to 1, so our solution doesn't blow up. But that's kind of hard to do in just this way. So what we actually can do is we can use the conjugate, the complex conjugate. Oops, I forgot a little I here. Sorry about that. Minus r minus IR sine kh. But that's okay now. So now we're all good. What we'd like to do is multiply g of k by the conjugate of g of k to get the absolute value of g of k squared. So that will be g of k. I'm going to write the conjugate as g star. That means wherever we have an imaginary number, we make it the opposite sign. So g star of k is cosine kh plus IR sine of kh. And the reason it's useful to multiply to get this kind of idea is because you'll have terms that cancel with each other. So it's very nice, times g of k. Okay, so let's do this together. We'll have cosine kh. I'm just going to write it out because it's always nice to have g star of k is cosine kh. Instead of minus I, will be plus I r sine kh. So we'll have cosine times cosine, which is cosine squared of kh. Then we'll have cosine times positive IR sine, but that will cancel with this cosine times this negative IR sine. So that's really plus 0. And then we have minus I squared R squared sine squared. So if we have a minus I squared, that's the same thing as plus, because I is the square root of -1. I squared is the square root of -1 squared. So that is going to change the sign really. So that instead of being a minus I squared, it's just going to be a plus everything else that is multiplied in the term. So it'll be plus R squared sine squared of kh. And you may say we're done now, and that's fine. I just want to provide a little bit of argument. Sine squared is going to be a non-negative number, because you square a number, it's not going to be negative. So we're adding a positive term to cosine, which is already bounded. And so the most we'll add is when r squared is largest. So the largest bound we can get is when r squared is 1, because you'll notice when r squared is 1, we have cosine squared of kh plus sine squared of kh when r is 1. And this is equal to 1 exactly, which is the most our growth factor can be. If we multiply by an r which is smaller than that, we'll have a smaller number than 1, so it will also be stable. So the Lax-Friedrichs method for our cute little hyperbolic linear partial differential equation here, ut plus cux is equal to 0, is conditionally stable when r is less than or equal to 1. Thank you very much for watching. I hope this video is helpful to you as you learn or maybe even make your own numerical methods. And I hope you have a wonderful day. Bye-bye.